Hello everyone, I am Dhara Kansara. I will discuss asynchronous or ripple or binary up counter in this video. So I will cover this asynchronous up counter. So first of all, we'll see the counter. What is the counter? Counter will count the clock pulse. So simply we are using flip-flops in this design. A resistor, this goes through a prescribed sequence of states upon the application of input pulses is called a counter. So resistor is basically, it uses the number of flip-flops. So in counter, we are using flip-flops. The input pulses may be a clock pulse or some external input and that of fixed interval of time or at random time. Counters are available in two categories, asynchronous counters and synchronous counters. Asynchronous counters also known as ripple counters. So in asynchronous counter, the clock input of some or all the flip-flops are triggered not by common clock pulses, but rather by the transition that occurs in other flip-flop outputs. Means in simple word, we can say output of one flip-flop will be given to the next flip-flop clock pulse. So previous flip-flop will operate the next flip-flop. But in synchronous counter, the clock inputs of all the flip-flops receive the common clock pulse. So one common clock pulse will operate all the flip-flops simultaneously. So this synchronous counter will fast compared to asynchronous counter because we are applying clock simultaneously to each flip-flops. Okay, now we will see different types of asynchronous counters. First, we'll see binary up counters. Asynchronous binary up counter. As I told you, asynchronous is also called as ripple counter. So the question may be asked like this, ripple binary up counters or asynchronous binary up counters or simply asynchronous up counters. Fine. So in this ripple counter, the circuit of this ripple counter, you can see here the circuit of the ripple counter. Here in figure A, T flip-flop is used and figure B, D flip-flop is used. 4-bit ripple counter, so 4 flip-flops are used, either T or D. Number of flip-flops is equal to number of bits we are using in the counter. Here I am using 4-bit. I'm going to design 4-bit counter, so I will use 4 flip-flops. Fine. Now, here suppose I am taking this T flip-flop first. We will see the operation of this T flip-flop. 4 T flip-flops are given. This is the input T. This is the clock pulse, but negative edge trigger clock pulse I am using. This sign indicates negative edge trigger. This is what? Clear signal, which will clear the flip-flop initially. This is the output. So in this circuit, what we are doing, the T input, all these T inputs connected to fixed logic, that is logic 1, high logic. So what is the function of T flip-flop? Whenever we'll apply T is equal to 1, it will simply toggle the previous state. Suppose previous state is 0 and this T is 0. Then we are getting same output. But this T is 1 and if previous state is 0, it will simply toggle the previous state, means at the output will get 1. This is what? Clock input. Fine. We are applying negative edge trigger clock pulse. The output of one flip-flop, output of this flip-flop will be given to the clock of next flip-flop. Output of this second flip-flop will be given to this clock. And output of this flip-flop will be given to this next flip-flop clock pulse. Simultaneously, we are collecting output here. And this reset signal I am applying simultaneously to each flip-flop, which will reset initially. This flip-flop will be reset by this reset signal. Okay, here in this truth table, I have taken only 9 inputs, okay, but here I am using 4 inputs. The total possible input combinations will be 16, 0 to 15, right? But here I am using only 0 to 8, okay? I mean, counting starts from 0, 0, 0, and I have taken only 1, 0, 0, 0. But here we are using 4 flip-flops, so counting goes up to 15. 1, 1, 1, 1. Then again, it will start from 0, 0, 0. So here what will happen? Suppose I am applying this count pulse, that is C. So initially, at the negative edge of this clock pulse, this flip-flop will toggle this previous state output. Now this output I am applying to this flip-flop, this clock pulse. Then what happened? At this negative edge, at the negative edge of this A0, this flip-flop will change its state. Then this output I am applying here. So at the negative edge of A1, this flip-flop will change its state. Similarly, at negative edge of the A2, this flip-flop will change its state. Okay, so you can see here, as I am applying A0 to A1, okay, so whenever this A0 will change its state from 1 to 0, then only A1 will change its state from 0 to 1. Why? When A0 is changing from 1 to 0, A1 is changing its state, because this is what negative edge trigger flip-flop. Negative edge means whenever clock pulse will change from high level to low level, this flip-flop will change its state. Means high means 1 to 0. So A0 will change its state from 1 to 0, means at negative edge, A1 will change its state from 0 to 1. Similarly, whenever this A1 will change its state from 1 to 0, this A2 will change its state from 0 to 1. Means whenever A1 is changing at 1 to 0, means at negative edge, this next flip-flop will change its state. This next flip-flop means this A2 will change its state. Similarly, when A2 will change its state from 1 to 0, here you can see 1 to 0, then the next flip-flop means A3 will change its state from 0 to 1. But at the remaining combinations, this will not change its state. Only at this edge, 1 to 0, this flip-flop will change its state from 0 to 1. Like this way, each flip-flop at negative edge trigger, all this flip-flop will change its state. Fine? So this is what 4-bit up counter. So now you can see here in this truth table, simply it will count the state. Counter will count the pulses. Means first of all the flip-flop outputs will be 0. Then this counter will change its state. I am applying here clock, right? Now, suppose this clock pulse will change its state from 1 to 0. A0 will change its state from 1 to 0. So at the same time, A1 will change its state from 0 to 1. Okay, so like this way, we will get the counting from 0, 1. It will start from 0, 1, 2, 3, 4, up to 15. Because I am using 4 bits. So highest count will be 15. Then after count 15, it will reset the circuit, means counting again it will start from 0 0 0. Fine. Suppose we are using 2-bit counter and I'm using here JK flip-flop, then the circuit becomes like this. Here this circuit is for 4-bit T flip-flop, 4-bit ripple counter using T flip-flop, and here I'm using 2-bit up counter using JK flip-flop. This is I have taken for your reference. Suppose in the examination the question may be asked like this: design asynchronous counter, 4-bit asynchronous counter using T flip-flop. So you can design like this way. Similarly, if JK flip-flop is there, then you are you have to use JK flip-flop instead of T flip-flop. So I have taken this example here. Like this way, you can design 2-bit binary up counter using JK flip-flop. Okay. So as I told you, 2-bit up counter, 2 JK flip-flop will use. Here, this is the clock pulse which I am applying here to flip-flop number 1, negative edge trigger. So at the negative edge, this output will change. Q will change its state, but right. So Q A will change its state from 0 to 1 because initially it is 0. So it will change its state from 0 to 1 at this negative edge. Fine. But what about QB? QB will be 0. But whenever I'm applying output, this output to clock pulse of this flip-flop. So negative edge of this output will change the state of this flip-flop. You can see here, negative edge of this output will change the state of next flip-flop, output state of the next flip-flop. So this will state it, this QB will change its state from 0 to 1 whenever this previous output will change its state from 1 to 0. At negative edge, this will change its state. So initially at first clock pulse, you can see here output is 0 0. Then after second pulse, means in this second clock pulse, output will be 1 0, means decimal equivalent is 1. Then third clock pulse, at third clock pulse, output is 0 1, that is binary equivalent is 1 0 and decimal equivalent is 2. Then at fourth clock pulse, both the output will be 1 1. So the decimal equivalent is 3. Then after fourth clock pulse, why after fourth clock pulse? Because I am using 2 bits only. So 4 possible combinations is there. So maximum possible combination means maximum possible digits. We can say binary number is 1 1. That is 4 0. It will start count from 0 0. That's why 1 1 up to 3. So 0 1 2 3. Then after this count pulse, this will reset the flip-flop, means counting will start from 0 0. Again, it will count up to 4. Then it will reset again. Then it will count up to 4, like this way. Okay. So here at the first clock pulse, this is 0 0, then 1 0, then 0 1, and 1 1. So this is known as timing diagram. This is very important to understand the function of this counter. Fine. Next, we will see 3-bit up counter. As I told you, 3-bit, so 3 flip-flop we will use. Here you can see in this timing diagram, 3 bits I am using. So maximum count will be 7, 0 to 7. 8 counts will be there. Total 8 counts will be there, 2 raised to n minus 1. But the total counts, I mean, it will count from 0, up counter is there. So 0, 1, 2, 3 and counts up to 7. Then again it will reset. Counter will be reset. So it will count, it will start from 0, 0, 0. This operation is similar to 2 flip-flop, 2-bit up counter. Okay. So this is what? 3-bit up counter. Okay, everyone. Thank you.